sometimes there's more than one way of distributing the valence electrons, even if atoms are connected the same way. So each of these unique ways is called a resonance structure. What that usually means is that reality is a hybrid of these resonance structures. Some resonance structures may be more significant than others, and we're going to talk more about that in the next couple of slides. Okay, but let's take a look at nitrite ion, for example. Let's draw the Lewis structure for this. Nitrogen, so we're going to put the nitrogen between the two oxygens. We'll talk later about why that's the case, but let's draw the possible resonance structures for nitrite, where the nitrogen is between the two oxygens. Okay, so nitrogen contributes 5 to the number of valence electrons. So it contributes 5 valence electrons. Each oxygen, if you recall, belongs to group 6A, contributes 6 valence electrons. There's 2 of them, so that gives you 12. And then you have a -1 charge, which contributes an additional electron. So 5 plus 12 plus 1, that would be 18 electrons. Okay, so let's distribute 18 electrons here. So what we're going to do is we'll start off by giving an octet to the terminal atoms, the ones on the end. So this oxygen needs 3 more lone pairs to get an octet. The other oxygen already has 1 pair, so it needs 3 more pairs to get an octet. So 3 lone pairs, 1, 2, 3. Okay, so now we have, you can see on this side you have an octet, on this side you have an octet. That's 16. Okay, so you need 2 more to get to the 18, so then the remaining 2 electrons will go to the nitrogen. There. So that's one possible resonance structure. And you'll notice in this particular case, the nitrogen is not following the octet rule. Okay? Now, you can give nitrogen an octet, and you might say that if we can get that nitrogen to have an octet, that might be a more significant resonance structure. That may be a more distribution that's more that reflects better the reality. So you can say, if I want the nitrogen to get an octet, I need to move one of these lone pairs from the end. For example, this one, I can move that to make that a bonding pair. So let me draw that here, where you have the double bond now instead with the oxygen. Okay, let me just put this in the same color. Have a double bond instead. So now this oxygen on the right will now have only 2 lone pairs, and then the nitrogen on the left in the middle will still have 1 lone pair, and then the oxygen here on the left will still have 3 lone pairs. Okay, so 1, 2, 3. So this is a situation where you have an octet on each of the 3 atoms. You might think this is probably a better structure because all 3 atoms are an octet. This oxygen has 1, 2, 3, 4 pairs around it. This nitrogen has 1, 2, 3, 4 pairs around it. This oxygen has 1, 2, 3, 4 pairs around it. So all 3 atoms have an octet. Well, is that the only way to get an octet of nitrogen? Well, from the symmetry you can see that it's also possible that it's this one that goes, we can move one of the lone pairs on the oxygen from the oxygen on the left instead. So what we'll have a double bond instead with the oxygen on the left. Okay, so the oxygen on the left, instead of having 3 lone pairs, will now just have 2 lone pairs. The nitrogen in the middle still has 1 lone pair, and the oxygen on the right, okay, the one over here, will now have still have a single bond and 3 lone pairs. Okay, so these are what you would call resonance structures of NO2 minus, and okay, because these are 3 different ways, we can draw double arrows between them to indicate that these are resonance structures, and then enclose all of them in brackets because this structure is supposed to have a -1 charge. basically what this means is chances are, okay, the nitrogen is the nitrogen to oxygen bond in reality is probably not a single bond and a double bond, but maybe something like a 1.5 bond between between the nitrogen and the oxygen. So this would be another way of representing the what we would call the hybrid. So this would be the hybrid representation of that resonance structure. Okay, so I still have my lone pair there. Okay, and I'll have right there. Okay.